Mike, you already did that.
Yeah.
Okay, give me a sec. It's gonna be live streaming in just a couple of seconds. Okay, thanks everybody for staying with us until the last lecture slash seminar for the third day of the summer, the second day of the summer school. So it's my pleasure to have here Virginia Aglietti, who is a four-year PhD student in statistics, supervised by Theo Damoulas at the University of Warwick, and currently she's an intern at Microsoft Research Cambridge. So I remember Virginia very well because she used to come to the summer. I mean, we first met when she came to the summer school back in 2017, perhaps. She was a student back then, and now she's given a lecture. So that's very good progress. So, okay, Virginia, is now your turn. Thank you.
Thanks, Mauricio, for the nice introduction. So it's a pleasure to be here. I was among the students 3 years ago, so I'm very excited about this opportunity. So today I'm going to be talking about some of my research that I've done in this in my PhD, and specifically I'll talk about multitask Gaussian process modeling for point process data. I should say that I'm finishing my PhD at the University of Warwick, and I'm a visiting researcher at the Alan Turing Institute, where I work as part of the air quality project. So let's start with a bit of an outline for today's seminar. So first of all, I'll try to give you a bit of a motivation and goal when we are looking at point data, count data, point processes. I'll then speak about some of the commonly used approach for modeling the intensity of Poisson processes with Gaussian processes. I'll then stop for a second and I'll give you a very quick introduction to multitask GPs that we need to look at multitask model for point processes, and specifically I'll look at the details of a model that we call the multitask Cox process model, MCPM model, that we introduced in a paper that was published last year in AI Stats. I'll then speak about inference in this kind of models. And for that, I will introduce and I will remind you what variational inference is for GPs with non-Gaussian likelihoods. And then I'll cover some of the experiments trying to show how these models can be used to recover the intensity function for real problems. Okay, so let's start with a bit of a motivation. That also was the motivation at the beginning of my PhD. Now, many social processes can be seen as point processes, and I'll give you some example for that. So the map here is the map of Cornwall, UK. So the data, the point that you see in the map are events of 4 different types of bovine tuberculosis events in the year 1989 and 2002, and different colors corresponds to different strains of the disease. And this plot is taken by this very famous paper by Peter Deagle, non-parametric estimation of spatial segregation in a multivariate point process. Maybe you're more familiar with these maps. These are quite recent maps. They are displaying on the left the counts for events of COVID-19 in the UK, and so we are speaking about number of events. While on the left, on the right, you can see the map, and I couldn't find one for the UK. This is a map of Tuscany, a region where I'm from in Italy, and you can see in red the exact geolocation for COVID events back in March. Another example that is different from diseases is given by in this map. So you can see here in black the events of, so actually the cases of assaults in the city of Chicago in the years 2004-2013. And this picture is taken from this paper, Fast Kronecker Inference in GPs with non-Gaussian likelihoods. Finally, in these 7 plots, you can see the counts for 7 different types of crime events in the city of New York in 2016. So we have burglary, felony assault, grand larceny, and so on and so forth. So we can identify some common elements in all of these examples. So first of all, these social processes are characterized by spatial and temporal correlation that may change over time in a non-separable manner. And especially when we look at different types of processes, like different type of crimes, we display cross-correlation, so correlation across different outputs or also tasks. So the goal for this seminar today is to look at how it's possible to develop a scalable algorithm that jointly model all of these processes while accounting for their complexities. Right, so I'll start by giving you an idea of what a Cox process is. So a Cox process is generally used to model and to estimate the intensity rate of events over a continuous space. So what's a Cox process? Well, in a Cox process, observed events are assumed to be generated from a Poisson process, and the intensity function of this Cox process is itself stochastic, and it's another random process with a given prior probability measure. So a common choice to model this intensity function is to use GPs, Gaussian processes. So the log Gaussian Cox process model, which is a very, very common model used for point process data, assumes that the intensity function is the exponential transformation of a Gaussian process. So if we consider an area A, the number of events that we observed in the area, so YA, given the intensity, is the exponential of the integral of this intensity function over the region A. Where the lambda x, which is a notation that is generally used for the intensity function, is the exponential of a Gaussian process. Now, the problem with this LGCP model is that the integral of this intensity function is generally not tractable. So what people generally do to do inference in this type of model is to consider a computational grid, generally a regular computational grid, but other more complicated grid can be considered as well. And the idea of a computational grid is that you have your spatial extent and you place a regular grid on top and you count the number of events that are falling within each cell, and you attribute that number of events to the centroid of the cell. So instead of considering an integral of the intensity function, what you do is you consider the number of events in a specific cell. This is like Yn, and this you assume to be Poisson distributed with the intensity, that is the intensity function lambda, computed in the cell centroid x of n. Now, this is only one of the limitations of the LGCP model.
Hi, Virginia, hi. Yeah. Is it okay if I interrupt with questions?
Of course.
Yeah, cool. Okay, there's one question already. It's a sort of initial question that should be asked at the beginning, I guess. So someone asked, could you define point processes?
Yeah, so in a very informal way, in a point process, you have events that are happening in time and space in a continuous domain. So for example,
okay.
Crime events or disease events or I don't know, another application, traffic events, and so on and so forth.
Yeah. Cool. Hopefully that's clear. Feel free to ask the question again with more details if you're stuck. And really quickly before I should let you get on because otherwise we can get derailed by questions. Can the grid be irregular, this computational grid?
You can be regular, it can also be non-regular.
Right, cool. Okay, fair enough. So right, we'll get back to we'll let you get back on it and I'll ask more questions later on because otherwise we'll get flooded by thousands of questions. So
yeah, so I should say that the picture that I have here, this grid here, it's a regular grid, but you can consider a more complex grid as well.
Yeah.
And it's an approximation because when you consider a grid, you consider the intensity function to be constant within a specific cell. I should also say that for those that are not familiar with point processes, you can think about Poisson process as a generalization of the Poisson distribution in which we have an intensity that changes over depending on some inputs, so this lambda of x, and it's inhomogeneous because the intensity function is not constant.
Yeah. Cool, thanks. So hopefully that answered those questions.
Interrupt me anytime. Yeah. I might
I'll hold off because like usually we get hundreds of questions, so I'll triage them a little bit. Cool, thank you.
Right. So as I was saying, so one of the main limitations of LGCP is that in order to have tractable inference, generally people consider a computational grid. But that's not only the only limitation because Generally, the LGCP has been developed for single task models. So with single task, I refer to the idea of considering only one output, one task, or one intensity function that we want to estimate. While, as we said before, we would like to have a model that jointly consider different processes. And another limitation is the fact that generally, and this is not always the case, but inference in this type of model generally proceeds with expensive MCMC schemes, sampling schemes, for which the inference is not scalable. So I will not focus on the problem of a computational grid in this talk, but you can find more details in this paper that was recently published at NeurIPS that focuses specifically on how to get rid of the approximation that is introduced with the regular grid or with the grid in general. What I will focus on instead are the second and third point. So I will cover how it's possible to consider GPs to develop a multitask model for this type of data. And I will also focus on how it's possible to develop scalable variational inference schemes for, again, GP modulated Poisson processes. Okay, so let me go back to the motivation that we introduced before and give you a bit of a motivation of why we need to use multitask models for this. So here you can see the first thing that you notice when looking at these maps is that different type of crimes display the same sort of spatial correlation. So the pattern that you see in the data for different type of crimes, it's very similar. So this type of crime or the intensity function of this type of crimes are very correlated. So we would like to learn a model that captures the dependency between these processes. This is a positive correlation, but you might also have negative correlation or spatial segregation, as Deagle is calling it in the case of bovine tuberculosis events, but we will see it later. Right, so let's stop for a second and let's look at what do I mean by multitask GP models. So far you've seen in the summer school in different form, you've looked at GP regression. So in a GP regression, you have a function that is modeled by a Gaussian process. You have a likelihood that is assumed to be Gaussian, and you collect some data, which in this case are given by these red dots in the plot on the left side. And you can write the multivariate distribution for the outputs that are observed. In this case, I have 3 data points, which is multivariate Gaussian. I'm assuming here a mean function of 0, and you have a covariance function that is computed from the kernel function and the inputs that you've collected. And what you can do here is to get prediction for a new test point by computing the predictive distribution, which in the case of a GP regression is available in closed form. Now, what happens when you have 2 functions? Well, it happens that you might see, for example, in this case on the left plot, that the 2 functions are highly correlated. So in particular, in this case, the second function, the blue one, is a specific transformation of the first function. So in this case, what you can do is you can place a GP on the first function and a GP on the second function. And then what you have is that you collect data point from the first function, and these are the red dots, and data point from the second function. These are the green dots. In this case, I have 3 points from the first, 2 points for the second, and I'm assuming the 2 likelihood for the 2 functions to be Gaussians as well. So how do you model these functions? Well, you can consider them to be independent, and this would correspond to having a multivariate Gaussian distribution for the set. So the notation here is these y1 are the points for the first function, these y2 are the points for the second function, and you can see that I'm modeling them independently because I have non-diagonal elements that are 0. So I have k1, which is the kernel computed for the first function, k2 with kernel computed for the second function, but I'm not capturing the correlation between the 2 functions. One way to capture the correlation between the 2 functions is to use what we call the intrinsic coregionalization model. Now, in the intrinsic coregionalization model, in the simplest form that you have a latent function, which is u of x, and you obtain the functions, the f of 1, f of 2, has a transformation with some coefficient of the latent function. So you have f of 1 that is w1 u of x, and f2 that is w2 u of x. So in this case, you can write down, again, assuming Gaussian likelihoods, the distribution, the joint distribution for these outputs as a multivariate Gaussian, where the kernel is given by the product of a matrix that includes all of the coefficients that are used to obtain the functions and the kernel of the latent function. So B is generally called the coregionalization matrix, while K is the kernel of U of X. Now, if we generalize this formulation, we can think about having P functions, Fp, and each function we can think about, we can model it as a linear combination of different latent functions. In this case, we have R latent functions that are all independent GPs with the same kernel, and each function f of p is obtained using different coefficient WPI. So once again, we can write the covariance structure between the functions, and at any 2 point x and x prime has a product of a coregionalization matrix and the kernel of the latent function, which in this case is assumed to be, all of the latent functions are assumed to have the same kernel. Now, this is only one formulation that can be adopted for modeling for multitask GPs. There are several extensions, among which we can consider different latent functions to have different kernels. And so we have the linear coregionalization model. We can have a semi-parametric latent factor model or process convolutions. I will not discuss these in this talk because I will focus on how multitask GPs can be used within a point process model. So the idea is still the same, and one of the first multivariate LGCP model was developed back in 2013, still by Peter Diggle, and the idea was to consider P type of points, so P type of intensity functions, where each intensity function, let's say the intensity function for the process P, is given by the exponential of 1 GP that is defined as the sum of two different GPs. The first one is a task-specific GP. This is f of p, and then there's another GP that is f of 0 that is shared across different processes. So the idea is that by considering this common GP f of 0, you induce correlation between different intensity functions. Yes.
Cool. Can I ask a quick question? Well, one question that came up earlier, I thought I'd just fit it in here, is in your model, or it depends which model we're talking about maybe, but is time one of the inputs into the GP that's being used to model the intensity?
You can do that. You can have a GP defined on latitude and longitude, so spatial coordinates, or you can also include time. So in some cases, in the one-dimensional, you could think about the x to be time. In the two-dimensional, I'm only considered just for you to see the intensity, I'm only considering two-dimensional inputs, but you could extend it to have 3. And actually, in the paper that we'll mention at the end, there are some applications to 3-dimensional spaces.
Cool. Okay. Hope that answered the question. Feel free to ask the questions again if you feel there's you need a follow up or anything. Cool. Thanks very much. Cheers.
Okay. Right. So again, this is one of the multivariate model that can be used for point processes. And as it was originally developed, Inference is this type of model was proceeding through a Mala algorithm, so a sampling methods that was making it extremely computationally intensive. Now, this is only one model. Another option that one has to model, to have a multitask GP model for point process data is to consider an ICM, so a type of intrinsic coregionalization model where the likelihood is not Gaussian anymore, but is actually Poisson. So in this case, the intensity function, lambda p for the p process is defined as the exponential of the linear combination of different latent functions. And the important thing to notice here is that the weights of this linear combination are deterministic and are generally optimized within your inference framework. So a Bayesian treatment of this type of model was proposed back in 2013, but again, Inference was proceeding through a sampling algorithm. So again, it was quite computationally intensive. So what we would like to achieve with the model that I'm going to introduce now is to have higher flexibility with respect to the multivariate log Gaussian Cox process model and with respect to the intrinsic coregionalization model type with the Poisson likelihood. But we also would like to have a fully Bayesian model that propagates uncertainty in the mixing weights of these latent functions. So in order to do that, we propose this model, this we call multitask Cox process model or MCPM model. That is, again, one of the many alternatives that have been developed in the past years to deal with this type of data. So again, in this case, we have Q latent uncorrelated Gaussian processes, as in the ICM model. But instead of having deterministic weights, we place a GP also on the mixing weights. And so the idea is that we have some inputs that could be latitude, longitude, or time. There are the inputs of our latent functions. And then we have some additional inputs that are, for instance, task descriptors that are inputs of the GP on the weights. So if you think about the crime application, you could have latitude and longitude and time has inputs for the latent GP, and you could have task descriptors. So for instance, how are these two crimes different? Are they mainly taking place indoor or outdoor, or in a specific time or not? So these are basically task descriptors that are capturing how the different processes are similar or different. So if we focus on this plate diagram and specifically on the red box in this plate diagram, the idea of this model is to consider this Q latent function with some inputs, space or time or whatever you want, and some weights that are again following a GP, where we again consider a GP as a prior, and we have these task descriptors together has the exponential transformation. They give us an intensity, and then sampling from the Poisson we obtain the counts. Now notice that this makes inference much more difficult because in this case, we have the exponential of the sum of the product of Gaussians. So we don't have all of the nice properties of the log Gaussian distribution. And we have to do something about it, basically. So as I said, this is only one of this MCPM model, but also the one that I discussed before are only some of the models that can be used to capture the intensity of point processes, because there has been a huge, a lot of research on this topic in the last years. So a lot of people have considered sigmoidal transformation for the Gaussian process, or even square transformation, thereby getting a permanental process. So I'm giving you some reference here. They're also listed at the end so that you can have a look at them if you're interested in getting deeper on the topic. Now, another big problem when dealing with this GP modulated Poisson point process is the fact that inference is not closed form. What do I mean by that? Well, you saw how when you have a GP regression, you have a prior on the function, you have a Gaussian likelihood, and then you can compute the Gaussian posterior in closed form. When instead you consider a point process model, the likelihood is not Gaussian. So you still have a Gaussian prior on the function, but your likelihood is Poisson, and the posterior is not available in closed form. So how do you deal with that? How do you compute the posterior and then the predicted distribution? Well, for approximate inference, you could use either sampling methods to obtain sample from the posterior, or you can focus on approximation of the posterior with something on known form, like for example, a Gaussian. And specifically, I will focus on the second option, and I will speak about variational inference. So I saw that you covered a bit variational inference this morning, so I'll just give you a bit of a recap. So the idea of variational inference is to minimize a divergence between the true posterior distribution, which is not available in closed form and is this P of F given Y, and an approximate posterior, which is of known form. For instance, it could be a Gaussian with some variational parameter mu and C. So what we want to do is we want to adjust the variational parameters of this distribution to minimize the KL divergence, which is given in this expression here. Right, so it can be shown that minimizing the KL divergence is equivalent to maximizing the evidence lower bound, which is a lower bound on the log evidence. So the idea is that we want to develop a variational inference algorithm that reduces the computational cost, especially when we have a high number of tasks. We want to avoid, therefore, mixing issues of MCMC methods that are, generally used for this type of models, but also we want to get rid of all of the further Monte Carlo approximation that would be necessary during the optimization procedure when we compute these elbow expression, which could be not available in closed form. So in order to do that, to develop a scalable variational inference framework, we introduced an augmented prior over the latent function. So what is an augmented prior? I believe you saw this morning how you can use inducing points to increase the scalability of GPs. So the idea is the same. We have an inducing process, which is this U, and we define it for we have Q latent functions. So we have Q inducing processes that are taking some inducing inputs. We consider M inducing inputs where M is significantly smaller than N. And then we can define a conditional for F given U as a Gaussian with updated parameters. So by defining this prior, we can then have our variational inference framework. And in this case, we have a true posterior and we have a posterior. So we have both the latent function, the inducing process, and the weights. And we can define a variational distribution Q of F, U, and W given some variational parameters. And in this case, we assume a variational distribution to be fully factorizable. Specifically, we assume a Gaussian distribution for this U and then a Gaussian distribution for this W. So very standard framework. The nice thing about these distributions, so this approach, is that we are able to get an expression for the elbow that can be computed without further Monte Carlo approximation. And why is that? Well, it can be shown that the elbow for this model is given by the sum of the two, so equation 2, 3, and 4. So you have your entropy term, your cost entropy terms, and then you have the expected log likelihood. And to compute the expected log likelihood, you need to compute the expected value of the log of P of Y. Now we saw how we have the Y is Poisson, and the intensity function is not a log Gaussian distribution anymore because we have the exponential of the sum of product of Gaussians. Luckily, it turns out that this expression can be computed in closed form. And it can be computed in closed form because this is equivalent to the computation of the moment generating function for the sum of product of Gaussians. So we have this very complicated expression, which is given in equation 8, that allow us to compute the expected log likelihood and thus avoid the need of black box variational inference framework. And thus we basically get rid of all of the further approximation that we might need in the elbow. And also we don't need, other methods that are allowing us to reduce the variance of the gradients in the optimization procedure. So overall, what we get, actually, let's go back to the terms so we can have a look at them, is that the KL divergence reduces in terms of distribution, in terms of it reduces the computation in terms of m-dimensional distribution. So this distribution Q of U is m-dimensional, same for P of U, and Q of W is of P dimension, but generally P, the number of tasks, is smaller than M. So we get rid of the distribution of n-dimensional distributions, and the expected log likelihood term factorizes in terms of n. So we can use stochastic optimization techniques to get rid of the dependencies also in the expected log likelihood term. So overall, the complexity of the algorithm is of order n cubic, which is pretty good. I would say that before going on, the idea of getting rid of the Monte Carlo approximation in the elbow computation is really useful in this case because the data are not very informative. So using black box variational inference has been, we show in the paper how it would significantly increase the variance of the gradients in the optimization procedure, slowing down the convergence of the algorithm. Right. Okay, so I'm done with the theory. I'm going to show you some experimental comparisons, and I'll show you three different methods. First of all, I'll show you a single task model. So the standard LGCP model that we saw at the beginning, where instead of our MCMC framework for inference, we consider a variational framework. Then I'll compare this to a variational formulation of the intrinsic coregionalization model, where we use a Poisson likelihood, and then this is very simply implemented in GPFlow. I'll compare the methods looking at the root mean square error, the negative log predictive likelihood, but also the empirical coverage. So the idea of the empirical coverage is that we don't only focus on the intensity function, on estimating the intensity function, but we sample from the Poisson, we sample from the posterior distribution on the intensity, and we recover an empirical distribution for the counts, and we check how the actual number of counts that we observed in the data is contained in this empirical count distribution that we recover. So the idea of all of these experimental comparison is to show the benefits on multitask methods. So the idea is to show transfer by generating areas of missing data and trying to recover the intensity in these, areas of missing data. Okay, so let's get started with some synthetic data. So for you to understand the setting that we are looking at. So we have 10 data points. So this is a point process. These black dots are giving you a point process, and we have 4 tasks, 1, 2, and 3, 4. And for each task, we have a different intensity. This is the gray line. So it's here, and then you can see here, you can see here as well. And for each task, we generate some missing batches. So we remove part of the data, so contiguous information, to make sure that the function, that the method doesn't know what is happening in the area. So it's forced to, share information from the other tasks. So the missing data are displayed with this red interval on the axis. And notice that these missing areas are generated in different parts of the input space. In this case, a one-dimensional example, so you can think about that, has time. And so the red line is giving us the MCPM model, so the model that we introduced. The green line corresponds to a single task model, while the blue line is the intrinsic coregionalization model type of model. And so basically, so if we focus, for instance, on task 2, you can see how the red line is capturing the true behavior of the function in the missing part, while the other 2 methods are smoothing over the data, and they don't capture what is actually happening in terms of true intensity function. The other thing to notice is that, for instance, in task 1, we generate missing data where this big peak is, but notice that the method does not see this big peak anywhere else in the other methods, in the other tasks, sorry. So is even like a multitask model, is just smoothing over the data and is not capturing the behavior of the 2 function there. So this behavior is confirmed by all of these metrics that we computed here. Overall, the MCPM seems to be a very flexible model that captures different intensity structure and outperform all of these competing approaches, especially in terms of CPU time. So it's significantly faster.
Cool. Can we just ask a couple of questions? There's one from Homero, who says, why can't we use multitask directly to model approximate point processes? So I wonder if there's a way of unmuting Homero so he could explain exactly what he means. Let me just find him. Does that work?
Yeah, hi, can you hear me?
Hi. Yeah, hi there. Hi, do you want to explain your question? Sorry, thanks.
First nice conversation, first nice presentation. Thank you for doing this.
Thank you.
So now my question, I wrote back to the question. What I was asking is, why don't we use multitask GPs directly to model these processes?
Yeah, because the intensity function is a positive. I should have mentioned it. Thanks for the question. The intensity function is a positive function. So you need a transformation for that. So the exponential is one of the possible transformation that you can use. But you could use the square. You could use the segmodal transformation. All of them are valid And indeed, different methods, different papers are dealing with different transformation and do inference in different ways depending on the transformation that is considered.
Okay, thank you.
So that makes sense. Pretty cool. And Stefan, did you have a question about the choice of? So I think it's about the weight and how you could use a more complicated function or something. Do you want to explain?
Yes. Yes, thank you. I was just wondering if there can be a more complex transformation than just a linear combination of weight and.
Sure. The problem with that, so you mean
the W's?
Sorry, yeah, I kept the question on hold for ages. Sorry, it's back.
This one?
Yep.
Yeah, you could use whatever, but you have to bear in mind that inference could become more difficult. So I was saying, in this case, inference is like so when you consider these weights to be deterministic and optimized within the inference, it's relatively simple in the sense that the expected log likelihood can be computed by exploiting the properties of the log Gaussian distribution. And just by even like only considering a distribution on the weights, because you have this sum of products, it becomes much more complicated, and you run the risk of having to use, you need to deal with black box variational inference because a lot of expectations are not computable in closed form anymore. And then you need to reduce the variance of the gradients, and you can use methods for that. But this is just a formulation that allows us to increase the flexibility while keeping some sort of computational tractability. So it's a compromise, but for sure you could use more complicated function. It's a bit like which one should you use then? It's a bit of an ad hoc transformation, which criteria you should use. That's not like a clear evidence in the literature telling you which model is appropriate in which case, which point process application.
Does that help?
Okay, thank you. Perfect.
Cool, brilliant. A couple of other questions have appeared as well. You mentioned, I remember on that slide where you talked about how it's analytically intractable and how you had to approximate the inference over which model was it? Yeah, exactly. So actually, Alex, I should have unmuted you. I'll just read out. Can you explain why inference in ICM or LCM is analytically intractable and requires approximation?
Because
is it somehow?
Sorry.
Yeah, no, sure. Yeah, yeah, exactly. I think you're going to say exactly what he says. Go ahead. Yeah.
No, go ahead.
Oh, just like, is it somehow related to non-Gaussian likelihood?
Yeah, exactly. So independently, so bear in mind that the thing on which we are, so let me go back. So when you look at the GP regression, you're assuming this type of likelihood. So you're saying the data point that I observe are noisy observation. You can also have non-noisy, but noisy observation of this latent function. Now, in this case, we have a doubly stochastic process. That's also why it's called doubly stochastic. So what we have, and let's go back to the LGCP. So what we have is that the GP is placed on a transformation of the intensity function, which is itself a parameter of the Poisson. So we have different layers, and that makes it intractable because you need to compute the expectation of the exponential transformation of a GP. And most of the time, or the Poisson transformation of the intensity of the exponential of a GP. So this makes it, in any case, in any time in which you have a Poisson likelihood or a non-Gaussian likelihood, this will be intractable. So even if we have like a classification problem, it will be intractable as well.
Yeah. Hopefully that clarified. Then there's two quick questions. One is on computational complexity, which is probably more general actually than, but yeah, for your particular implementation, what would because you're doing the closed form and stuff as well. It's kind of like, I guess it's kind of complicated because it depends how many. The thing that also matters is the number of iterations of stuff you need, right? So it's kind of going to be hard to measure. But sorry, do you want to answer the question? Sorry.
Yeah, so at every step, so here I'm giving the complexity for every step. It's not the total one. I'm not considering the number of epochs that I run the variational inference for, because it depends also on the application and whether the model is converged or not. But in general, the complexity of order m cubic, because again, this KL divergence depends only on a distribution that are m-dimensional or p-dimensional. And because you have this summation over n for the expected log likelihood, you can use stochastic methods for that. The nice thing is that independently on the computational cost, you don't need any other methods on top of that for gradient reduction. So having this closed form is not really helping you in terms of computational costs. What it's helping you with is the fact that you don't need, you don't have the problem of additional approximation or error that you introduce by using Monte Carlo.
Oh, right. Yeah, of course. Cool. Okay. And then finally, one easier question maybe is code and repo. So where would people go if they wanted to either run your code or if they wanted to implement it themselves?
Yeah. So I'm mentioning a paper at the end. The paper has the link to the code that is available on GitHub for this specific method, and it's also, you'll find there also the code that has been used for the benchmark. So if you're just interested in implementing a standard LGCP methods with variational inference, it's all in GPFlow and you can do it very easily.
Fantastic. That's really good. Wonderful. Cool. Thanks very much. That's all the questions for now. Hey, I'll let you get on. Hey,
Let me think. I forgot where we are. Oh, okay.
Sorry.
Yeah. So these are the synthetic experiments. The same type of reasoning will be used for the real data that I will show you now. And for the real data, we will have a two-dimensional input space. Okay, so first data set that we analyzed, and you will find in the paper, is the crime data set that I mentioned at the beginning. So in the first row of this plot, you can see the observation for different crimes. So you have 7 different types of crimes. And what we do is we generate patches of missing data in the spatial region. So these shaded areas are data that we completely removed from the data set. And the idea is that we want to see what happens in this missing data region when we use a multitask model or a single task model. So the first row corresponds to our MCPM model. The last row corresponds to a single task model. So if we look, for example, at felony assault and focus on this specific data region, so the shaded region, you can see how a multitask model is able to recover the value of the intensity function, or approximately the value and then the intensity function in this region, while the log Gaussian Cox process model is just smoothing over because he doesn't share any information from with the other task. So it's just going to say the intensity is 0. Same happens across the different methods. You can see, for example, here. So here we have, again, an intensity which is basically 0. Same happens here. That's a very, very weird behavior of the LGCP model. And something to notice is that all of these crimes, they have different magnitude, meaning different total number of events that are observed for different crimes. So it's very different. Like we have like 2,000 cases for grand larceny, and then something like 93 for grand larceny of motor vehicle, but still we are able to recover the same type of like the overall rate and the behavior, the pattern in the spatial region. So this aim is confirmed when looking at the metrics. Once again, the MCPM model, the model that you proposed, seems to outperform the other methods. And something interesting to notice is that the CPU time is significantly lower even compared to the ICM model. So the LGCP model is lower, but it's a single task, so that's where we would expect. The ICM is a multitask, but our method is significantly faster because for the ICM, you're considering the complete matrix that you need to invert, which is the number of points times the number of tasks. So assuming that you're using inducing points is a matrix of dimension m times p times m times p. So it's, well, in our case, because we keep this different view on the functions and the weights, the complexity is m cubic. Now, let's look at the last example. This is, again, one of the examples that I mentioned at the beginning. This is a bovine tuberculosis data set, which is very common in geostatistical papers. So, yes?
I was going to quickly interrupt. There are 2 questions I was hesitating to interrupt though, on the last slide, sorry. One of them is, someone was asking what X and Y were. I assume it's latitude and longitude, or easting and northing or something. Is that what?
Sorry?
I assume it's... they're asked what X and Y axes were on the slide, which I assume they're
so this is like X. So this is X1 and X2. These are latitude and longitude.
Yeah. And the other comment was about why was the motor vehicles, grand larceny for motor vehicles overestimated? What's the, for both models? What was the, is that true, or is it just like an artifact of the visualization, or is that...
I didn't get the question, sorry.
Sorry, the grand larceny for motor vehicles seems overestimated for both models. And I'm just wondering.
Yeah, I think that's because compared to all of the other tasks, it's the one for which we have the lowest count. So if you look at the scales of the other counts,
that's interesting.
It's 4,000. Yeah, so there's a bit of a overestimation true, but we saw them in all of the methods because the scale of all of the others are extremely different.
Yeah, that's odd though. Okay, cool. Yeah, I guess it depends with a different count. I don't know. Yeah. And another question has appeared. Does the model generate a predictive distribution or point estimate? Okay.
Yeah, predictive. So it's a Bayesian model. So you can get a predictive distribution. It's generally obtained by sampling from the Monte Carlo. So you sample from the intensity. So you have sample from the GP at your predictive, the point that you want to compute the prediction. Then you sample from the intensity, and then you sample from the Poisson. So you can get a prediction for both the intensity with some uncertainty bounds, and the same for the counts.
Fantastic. Cool. Thanks for that.
Yes.
Yeah.
Okay. So last application is this bovine tuberculosis dataset. So this is interesting because it's different from the crime dataset. So in the crime dataset, you could see that you were displaying already by looking at the data, you could display some sort of like very similar pattern in the data. What you can see here in this application, and this first row represents the data, it's what Peter Deagle calls spatial regression. So what we have is that, so this GT9 corresponds to a specific strain of the disease, is genotype 9, and this genotype 20. So the genotype 20 is generally observed in the south part of Cornwall, while GT9 is observed in the north part of Cornwall. So we can see how different strains of the disease are obtained in different regions. It's very separate, let's say, in terms of a spatial pattern. And here, instead of looking at a multitask and single task, we see how, so in the second row, we give the multitask Cox process model. In the third row, we give the intrinsic coregionalization model. So the first thing to notice is that we avoid, in a sense, negative transfer. And the two models compare really quite closely. What we seem to observe, but again, these models are in this case quite similar, is that in this specific shaded region, so in this specific missing data region, the intensity function for the MCPM seems to be quite close to 0, while in the other case, it seems to be a bit closer to the data for the ICM. In all cases, so when we compute the performance, we average, so we run this model moving around the shaded region. So all of the numbers that you see here, but you saw also in the tables before, obtained has average over the different configurations and different random seeds. So overall, it seems like on average, our model seems to perform better than the ICM model. But the nice, interesting thing is that one epoch runs in 7 seconds compared to 67 seconds or more than a minute. All right, so I'll conclude with some, a summary of what we discussed today. So multitask GP models capture the correlation of different social processes, and different multitask GP model can be used to model the intensity function of point processes. The model that we propose is multitask Cox process model, allow us to increase the flexibility with respect to a standard multitask IGCP model or a ICM type of model by introducing these stochastic weights, and therefore offering also a fully Bayesian model that propagates uncertainty. Posterior inference in this type of model requires approximation because the likelihood is Poisson, and this scalable inference can be developed by taking this separate view on the function and the mixing weights. So this is the paper that deals with all of these methods that I spoke about, in giving you also a nice related work section with references to all of the papers that I mentioned. This is joint work with my supervisor Theo Damoulas and my collaborator Edwin Bonilla. And I'll conclude with a bit of a teaser. So we saw how different models can be, different GP models can be developed to account for correlation across intensities. What if you want to develop a multitask model that incorporates a specific correlation structure that is given in a causal graph? We'll discuss about this tomorrow, so I'm looking forward to see you all there. Thank you.
Cool, thanks very much. That's really great. Feel free, there's a few minutes spare, so if anyone wants to ask any questions, feel free to post them now. There's one question that's currently outstanding. They were just asking about what's an epoch in runtime reporting? So what did that mean?
This is the number of seconds that it takes to do one complete iteration of the variational inference algorithm, so in the optimization procedure.
Cool, hope that was cleared up. I just didn't want to, I'll leave it to you to answer just in case. Ask. Normally there's thousands of questions. People are too stunned, it seems, to ask. Well, hopefully they can actually ask questions. Not a permissions problem. That's cool. So can I quick, oh, okay, okay. So the lecture slides are available. We'll put them on the webpage. Hopefully they're there now, or they'll be there soon.
Yeah, I'll make them available.
Cool. So someone's asking about using stochastic variational inference. So actually, Leah, I'll just unmute you and let you ask, because you might have a particular angle that you want to ask this from. Too many people. Cool. Yeah. So Leah, do you want to sort of ask if there's a particular application you have in mind?
Nothing specific. I'm just thinking about stochastic variational implementation. I know that we're talking usually with time-related data, so I'm not expert on time series or point-to-point processes. But are you aware of any approaches that might be speed up your computations, or maybe do the life easier by using SVA instead of just variational inference?
No, actually, we didn't use it. So all of the results and the performance that you see here are not using it. But when we wrote the code, we realized that was an option, and we just use mini batches, like randomly selecting a bunch of points at every epoch.
Perfect. Thank you.
Cool. So I was asking about this is a huge question. What are some other general applications where multitask GPs can be applied? So that seems like
this is a huge a huge number of applications. Well, the teaser that I just gave you, it's another application.
Yeah.
Very, very different application. So the idea there is you run experiments in a system, and you want to capture their correlation in a way that when you perform an experiment, you can infer or have a distribution about what would happen if you were to perform another experiment. This is also a multitask model. So or you can just think about GP regression. For instance, I'm thinking about sensors applications. So for instance, you have sensors that are like in a city, and you have some missing observation for some sensors, but you know that the characteristic of the location is very similar. So it's similar. The location is similar to what you've observed. So you can use that to infer what the value would have been for that sensor that is missing. And there's like a GP regression case.
Yeah. That's a bit like I'm messing with this problem of trying to calibrate low-cost sensors with reference instruments across the city. So that's sort of, basically.
Something that we use it for at the Alan Turing is to model air quality. So we have different pollutants in a city, and we want to infer the level of all of them, and we might have some missing values because the sensors are broken or they're not calibrated, and we use multitask models for that.
More questions? I should probably let people ask them, but anyway. So can high dimensional input data be used in multitask Gaussian processes?
Yeah, I mean, you're using a GP, right? So you can use high dimensional data point for GPs, then you will have some problems, I don't know, in terms of inference maybe, but in principle, you could do that.
Yeah. It's got the same restrictions, I guess. And Homero asks again, what are your suggestions to generate the predictive distribution of nonlinear transformations of GPs?
What do you have?
Yeah, let me unmute Homero so he can ask this directly, so I don't have to guess what his question means. There you go. Hopefully you can talk.
Yeah. Hi again. Hi.
Thank you.
Thanks for giving me the chance again. So I am working in a trying to use GPs for multi-objective optimization. And in one approach, what we do is like we find the maximum between different GPs. So if we apply the maximum of different GPs, we end up with a model that is no longer a GP, right? So I was wondering if you can suggest some techniques to generate predictive distribution for such a nonlinear transformation.
I don't know about the maximum, but you can still use Monte Carlo to sample from the predictive distribution. So, I mean, that's the simplest thing that you can do.
Yeah.
Okay. I don't know if there's something like specifically closed form that you can use for the maximum, but if without, the first thing that you should try and see whether, maybe the Monte Carlo has a problem because it's very expensive to compute or it has huge variance, but you could just sample from the GP and then take the transformation and get a sample from the predictive distribution of the max.
So if I am dealing, let's say, with 2 GPs or with 3 GPs, and what I want to do is like at each predictive point, I want to predict what is going to be the maximum, because I want to find the point that minimizes the 3 functions in the whole design space. So for that reason, I wanted to generate that predictive distribution so that I can use Bayesian optimization.
Yeah, but it depends. Like, are you using a multitask model for that?
I am planning on doing that.
Yeah.
No,
because then you could sample all at once, right? And then model correlation. But I don't know how you would. I will have to think about it.
Okay, thank you.
Sorry about that.
No, yeah, thank you.
Cool. Somebody, but unfortunately, says anonymous, so I can't ask them to answer or elaborate. But no, they said you mentioned about your air quality work at the beginning. Could you elaborate a bit on that? I don't know exactly what feature of your work they wanted you to elaborate on that. So, whoever it was who posted, could you post another question with so we can unmute you and you can explain?
I would be very happy to share with you the publication that came out of that work. It's focusing on multitask model for what was that? Non-regular. Let me look for it.
Is this with Ollie? Is that right?
Yeah.
Or is that a different? Yeah. Cool.
Yeah. So I'm not directly. I mean, part of the project. The idea again is to use GP to estimate the value of different pollutants in the city and to use sensors for that. But I wouldn't. I mean, it's not directly my work, so I wouldn't want to, say something wrong. But I'm happy to share the details of that.
Yeah. Cool. Let me just unmute Yao and get them to ask their question. There's too many people. It's hard to find. There we go.
I can see a question.
Yeah, I've just unmuted them so they can ask it. Yao, do you want to? If you can speak, then hopefully you're unmuted. Well, okay. Well, anyway, yeah. How do you sample the data to build a model? Is the question.
So you generate this. Okay, let me look at. So this is. Okay, so the synthetic. So in the real data, we have counts. In the synthetic case, so we have, I believe, I don't remember exactly, but we have 2 latent functions, and we generate the intensities a linear combination of these intensity functions with some coefficients, and then we sample from the Poisson.
Hopefully that helps. Feel free to unmute if you can. Yeah. What other questions were there? Trying to think if I can find more. I was trying to think my own work with what you were doing. But I don't know. Again, it comes back to this idea of using a more complex function, maybe for the rather than just a weight was actually something I was interested in as well, just because that was for calibration though, and it's because often the low cost sensors have a unpleasant, like nonlinear sort of like responses in their stealing effects and things. But my experience was that it just got too, like the model complexity just got too bad for the data that was trying to fit it. So was that what that was your problem, I guess, when you tried that?
Yeah, we tried to, we wanted to have efficient inference. That was the problem that we were dealing with. So we wanted to have compromise between the two. That was the whole idea.
Yeah, exactly. Yeah. That's really clever. Yeah. Okay. Yeah. Oh, okay. Zeal was the person who asked. Okay, cool. Sorry about that. Cool. Any other questions? Got another few seconds to ask. Otherwise, I guess we're about out of time. So, okay, cool. Well, I think you can hear the round of applause. You can imagine it anyway. I should get some canned applause for this. Anyway.
Thanks for the question, everybody.
Yeah, no, thanks, guys, for the interest and stuff. It's a really cool area. And thanks for the talk. I think I've learned a lot. And all the slides will be on the webpage if they're not there already. So
I'll make them available straight after the.
Fantastic. Cool. Hi, Maurizio.
Yeah. So yes, Virginia, thank you for the talk. So yeah, I think we are then finishing the second day of the summer school. And yeah, tomorrow will be the last day of the summer school, and then we'll have the workshop on Thursday. So looking forward to the lectures tomorrow, and yeah, see you tomorrow then. Thanks, everybody.